Today we're going to talk about a self-calibrating method to certify performance of a motor without using a loading device like a dynamometer. This is the Mds Portable Dynamometer, a product introduced in June of 2018. Edward Deming was the father of modern statistical quality control. His mantra was, "In God we trust. Everybody else has to bring data," which was a good idea because these days it's all about data. Big data this, big data that. Everyone wants data. In our field, motor testing, we're always interested in a better way to test our motors. Most people are familiar with the idea that all physical processes and happenings involve imprints or leave imprints on the devices and surfaces that they touch. One of the more common examples is the science of firearm forensics, which everyone's heard about. And that science, which was developed in the 1800s and the early 1900s, the invention of the comparison microscope in 1925 revolutionized the law enforcement industry's ability to track crimes and firearms used in crimes. These days, that kind of work is done automatically through the computer, of course. Some similar pictures are taken, but all the surfaces and minute marks, which are much finer than what could be seen with those optical microscopes, of course, are now all analyzed automatically. And furthermore, the discipline of statistics has replaced the subjective, almost all the subjective aspect of that pattern recognition topic, resulting in some of the things we use today every day in our regular lives. Our challenge as an engineering organization has been to confirm the performance and signature of any motor without a dynamometer. In other words, identify its fingerprint and the parameters that make up its unique fingerprint in a way that's self-calibrating and therefore unassailable. A lot of people have worked on a topic like this, but typically what happens is people always wonder about the quality of the data and how we can validate that the information is correct and the performance curves are correct. What we're going to show you is 16 elements of a calibrated motor signature that illustrates the consistent as expected performance of that motor. To start, we're going to generally rely on making uncoupled starts of motors. Here we see a couple induction motors. What we do is we place a speed measurement device or a shaft encoder. It's this small cylindrical device here with a magnetic attachment onto the end of a shaft. Here we see a 100 horsepower motor. Here we see the same device attached on the end of a shaft of a 1 horsepower motor. In the right-hand case, we've added a pulley onto the shaft simply to have enough landing space for the magnetic coupling. We then center the coupling on the shaft so it won't wobble and give us erroneous results, and we start the motor. When we start the motor and record the speed with that device, the startup curve looks like this. The power comes on at T0, it reaches full speed at T1, stays at a no-load full speed condition for several seconds, 5 or 10 seconds in this case, and then we cut the power to the motor, at which time the motor coasts down normally with the inertia of the rotor driving through the friction, which is mechanically slowing down the rotor. From this basic recording, under several conditions that we'll talk about in a few minutes, we can derive almost all the interesting parameters of a motor. And let's proceed and we'll show you how. The first thing you notice is that the slope of that curve. During the startup portion, this line represents the slope of that curve we just looked at. So it looks, in this picture, it looks like almost a straight line, but in fact the slope is changing. And you'll see there's a little bit of oscillation in the speed as it gets to full speed. And if we zoom in on that, we notice that the slope actually matches the shape of a torque speed curve pretty much. As it gets up to speed and the current drops off and the motor begins to run close to its synchronous speed, basically the only torque is just a little oscillating torque as the inertia of the motor bounces on the electromagnetic field slightly. And as the power is cut, then we see that the acceleration goes negative, indicating that the motor is slowing down. We're all familiar with Newton's equation, F equals ma, which represented in the rotating domain is torque is inertia times acceleration. As we see here, it turns out that if we don't have any load on the motor, in other words, it's not coupled to anything, the only thing impeding the rotation of that motor is friction and windage and losses and other losses, mechanical losses in the motor. So the inertia of the rotor does not change during a start, so the inertia is a constant. So if we knew the inertia and we measured the acceleration like we did here, all we'd have to do to get the mechanical output torque curve of this motor at the voltage we tested it at would be to multiply this acceleration curve times the inertia, and we would have the mechanical output torque. This is the fundamental idea behind the portable inertia dynamometer. So when we do that, this is the kind of thing that we get. This is the kind of result we get. Here is a 250 horsepower, 460 volt 2-pole motor, some performance curves. This is a typical start for that motor. We have we run the motor up and it runs up. We start it, runs up to full speed, oscillates a little bit after it gets to full speed, then stabilizes at full speed. If we look at the torque, which again is the slope of this line, there's a lot of noise when you do a differentiation of a curve like this numerically. So what we've done is the red line is averaging out the acceleration. We multiply that by the inertia of the motor, and we get the torque in Newton meters, between 600 and 700 Newton meters during the start of this motor. And as you see, there's a little bit of oscillation. Here's the oscillation in the speed and the resulting oscillation in the torque as we get up to high speed, full speed. So we repeat this exercise at multiple voltages. The reason we want to do this at multiple voltages is so that we can characterize the losses in the motor. In this case, you see we've had a power supply that we could set at various settings from 100 up to 460 volt, line to line, and we started the motor 5 times. Here are the resulting start curves. It turns out that this is about what we'd expect. Obviously, the higher the voltage, the faster the motor starts. But there's some interesting math tricks we can play on this data to analyze it a little bit further and show that it's consistent. In this view, the motor doesn't necessarily prove to anyone that it's acting consistently. But if we normalize the x-axis to the start time and plot it in log-log, it turns out that for very good physical reasons, which we won't go into today, these start curves overlay each other right on top. And it turns out that this is one of the characteristic elements of a consistently operating and properly operating motor. That is, no matter what line-to-line voltage you use to start the motor, the behavior of the motor in this kind of a view will always be the same. So this is our first element of a signature. Turning now to the line voltage and line current, the next thing we see on the left here is the motor terminal voltage. This is the average RMS voltage of the 3-phase RMS voltage that's applied. You see here in the last run at 460 nominal volts, during the start, there's quite a lot of voltage sag due to the resistance in the power supply and leads to the motor. In fact, the line-to-line voltage that's developed at the motor terminals is well below the nominal line voltage. This is a characteristic of the facility's ability to deliver power to the motor. Similarly, you see the same characteristic at every voltage we test the motor. And so we see an opportunity here that we can possibly normalize these results, which we'll see in a minute. And you notice also that at power off, we see a similar coast down effect decay effect of the motor's terminal's voltage. This is because when you power off a motor and it's spinning down, the motor actually generates back EMF, which we can measure and detect with the appropriate placement of our voltage sensors. Line current, on the other hand, behaves similarly. This dashed line is the rated current of the motor. If we start the motor across the line at 100 volts, the inrush current is a little bit, just slightly above rated current. But if we start the motor at 460 volts, its rated voltage, we notice that we get an awful lot of line current, 5 or 6 times the rated current, which is what we expect. So let's look at this a little differently. Here's an example of how the real-world supply impedance, which is the combination of the leads in the motor, leads to the motor, and the behavior of the power supply upstream of the motor, how it affects the voltage sag. At very low voltage, we don't get too much voltage sag, and at higher voltages and intermediate voltages, we get different amounts of sag. That's an indication that in this case, at this facility, the supply impedance was different at every voltage. And the reason for that was simply because there were different taps, different placements on a variable tap transformer used to power the motor. And we can document the supply impedance using this technique, another element of our signature. Moving forward, if we plot the terminal volts and line current on the vertical axes here versus speed on the horizontal axis, we see that at every voltage, we can compute the intercept of the curve along the zero speed axis, the vertical axis here at zero speed, and that point is called the lock rotor parameter. So for example, this one on the right, on the line current, when we were testing at nominally 380 volts across the line, the line current that was developed, the lock rotor line current, looks like it was around 950, 975 amps, something like that. Similarly, our locked rotor voltage for our nominal 460 volt start, actually at locked rotor or zero speed, the voltage had sagged all the way down to about 380 volts. And as the current drops off, as you see on the right side, then the voltage rises because there's not as much voltage drop due to the lower current, and the voltage stabilizes at the nominal test point. So anyway, what we do for all these runs is we identify the locked rotor voltage and current for each run. What we can do then is another element of our signature is to ensure that the locked rotor current versus the locked rotor voltage on the horizontal axis, if we plot each one of those points for each one of those runs, we expect those to fall on a nice clean power curve. This is another elemental behavior of a motor. This is not expected to be a straight line due to nonlinearities in the motor. Similarly, if we look at the locked rotor power, or watts, versus locked rotor volts, we see another power curve emerge, and the data looks pretty clean here. Another element of our signature. This, again, is an illustration. The exponent of this curve, by the way, is not 2, so the power increases faster than volts squared, which we haven't shown in this picture, but it's an element that we have the motor's behavior that we measure as another indicator. Similarly to power, we would expect acceleration to increase at a similar rate to power. So this is the locked rotor acceleration, in other words, the initial RPM per second that the motor starts up with. Another element of the behavior, and you see it lies on a pretty nice clean curve there. If we take those and a couple other ones, we find out that in a similar way, all the power related quantities have a consistent slope versus voltage and log. That slope is this exponent that we saw in the power curve in the previous 3 slides. And we note that the line current versus voltage has half of the slope as we expected. This is another element of our signature. Another thing we can look at is the residual motor terminal voltage after we power off the motor from different voltages. The vertical axis here has been normalized to the voltage at power off event. So that's all divided, in other words, just divided by the voltage. So this is always 1. And then we notice that all of the curves lay on top of each other. This is another mechanical characteristic of the motor. And if you think about it, no matter how you run the motor, if you run it at the same frequency, an induction motor, it'll always run at the same no-load speed or very close to the same no-load speed. And since it always coasts down from that same speed, regardless of what voltage you use to run the motor at, you would expect that the coast down curves should overlay, unless there's some very significant temperature dependent effect in operation between runs, which we do not have in this case. So another element of our signature. You can also look at the input motor impedance, in other words, the impedance that the power supply sees at the motor terminal looking into the motor. And we notice several very, very interesting things here. We notice that the impedance is a function of the input voltage. And in fact, that's correct. Physically, what's happening is the nonlinearities are distributing themselves primarily due to phenomena like eddy currents and deep bar effects in the motor at various voltages. And there's quite a steep change in the behavior of the impedance as we approach synchronous speed. Coming back to our speed coast down curves, here are our normalized coast down curves again for 2 different motors. The one we looked at a moment ago is our 250 horsepower 460 volt 2-pole. The motor in the right is a half horsepower 460 volt 2-pole. What we notice is that the slope of the coast down curve is dramatically different in these 2 motors. And what's happening is that the no-load friction in this motor on the right was measured at a steady state no-load condition to be 22% of the rated output power of the motor at rated voltage. That's a lot of friction in that motor. And in fact, it turned out when we went back and investigated, the motor had been repaired and reassembled, taken apart and reassembled incorrectly with a slightly cocked bearing in one end of the bearing housing. In this case, in our large motor, this is more like the kind of number we expect for friction and windage at no load. And this is the kind of a coast down curve you get. It takes a long time, many minutes typically, for a serious motor to coast down in a no load condition, because the power dissipating the energy and the kinetic energy of the rotor, causing it to reduce speed, is less than 1% of the rated power of the motor. So it's a pretty clean motor. So this dashed line here is what we call our time constant level. So the time at which this curve crosses this line is defined for decaying electromechanical phenomena as the time constant. So we simply define what that time is. In this case, it's well over 30 seconds, probably more like a minute. In this case, it's like around 1 second. This is the horizontal axis here on these curves is seconds. So in about 1 second, this motor had achieved its 63% level for coast down, indicating very high, confirming, I should say, very high internal friction and or windage, which can be separated, but we won't go into that now. Another interesting characteristic we can pull out is when we look at the no-load power from these multi-voltage runs, if we look at the nominal voltage along the horizontal axis here, it's the no-load voltage. The power that's graphed here on this line is the power in watts that's had the mechanical friction and windage power subtracted from it. And what's left at no load is the core loss watts. So if we graph this, you'll notice the vertical axis is log, the horizontal axis is linear. The It turns out that the characteristic core loss versus voltage function is supposed to be a straight line in this representation. And in fact, it's pretty close to that. So this is another characteristic of the motor, our ninth element of its signature. Coming back now to the residual magnetism signature and the voltage decay transient, we notice if we graph the decaying voltage in vertical on the log axis and horizontal on the linear axis, we note two distinct slope signatures. It turns out the first slope is the slope of the decay of the flux field in the motor, as the flux field, which can't decay instantaneously when you power off a motor, decays. And then the second slope that it settles into after several seconds, almost 15 or 20 seconds in this case, is the actual back EMF, which is caused by residual magnetism in the rotor generating voltage. Now you'll notice here we started at about 460 volts, and by the time we're 10 seconds or 15 seconds out, we're down well below 10 volts. So this is not a large voltage, but it certainly is measurable with the right kind of test equipment. And separating out these effects constitutes another element of our signature. Another interesting thing we can calculate from these data is the rotor inertia value. We can calculate it independently from the electrical and mechanical voltage recordings. On the left, we see the inertia from the torque equation during mechanical data during power coast down, and we see what we expect to see is that this is a straight line, and in this case it's a straight line after a certain decay part of the curve here, but it stabilizes at about 1.2 to 1.3. This is kilogram, the inertia measured in kilogram meters squared. Similarly, during the startup, this is during the coast down, time since power off. During the start, we can actually calculate using energy equations where we're measuring the energy in because we're measuring the power by calculating the power in watts and the power factor, and integrating that, we can get the energy input. We can subtract out the energy due to the losses, which we saw a minute ago, friction and windage and core loss, as well as the I squared R loss. And if we form the correct math, we in fact get another estimate of the rotor inertia, which in this case is about 1.2, which is pretty similar. Another element of our signature. Another element of our signature is the torque and the acceleration torque, in other words, the output mechanical torque causing the rotor to change speed. That's the mechanical output torque divided by the input watts. And now in this case, we can actually place a rated data point on this curve, and we see that in fact the motor is behaving normally, passing through the rated point of the motor. Also calculate the efficiency, which is defined as the mechanical output power divided by the electrical input power. We're measuring the electrical input power, which is just watts. We're measuring the acceleration times the speed times the inertia, which is the mechanical output power. We just divide the two and we're done. We can also assess how the real-world voltage, supply, impedance, and winding resistance affect our results. In this case, on the left, these are the measured individual three-phase currents on the bottom and the voltages on the top. Excuse me. On the right, we form, since we have the three currents and voltage, we can actually form the percent unbalance of those three readings. And we see that the percent voltage unbalance is not too bad. It's varying between about 0.5 and 1%, but we notice it's oscillating. The reason it's oscillating is that at this particular facility, there was something going on in the power distribution system that was pulling power from one or more phases, causing this oscillation in the voltage, voltage to the motor. You can see the oscillation on the left present in the voltage supply. The orange curve here is the unbalanced current, which we expect to be much lower during starting than during an unloaded condition. Another element. This technique for starting, we're often asked if you are forced to use across the line starts. The answer is no. This works with across the line starts, stepped starts like in the upper right, ramped voltage, constant frequency starts like with a Phoenix power supply on the lower left, and it works with constant volts per hertz starts, a variable frequency drive. We won't go into the details now, but suffice to say that the analysis is a little bit different, but the end results are the same. Finally, a few comments on the accuracy and reliability of this technique. Accuracy and reliability are two parameters that if you have a group of estimates of some quantity, there is a mean of the estimates and there is an offset from the true value between the mean and the true value. That offset is the accuracy and the scatter is the repeatability or the variability of the result. In this world of motors, here's a graph from the IEC. We're often asked how closely these results match nameplate because that's most people are most curious about whether the motor is doing what it's supposed to be, and their reference for what their motor is supposed to be doing is typically the nameplate because that's usually the only information they have, unless it's a large motor, in which case you may have factory measured data or a factory produced data sheet. At any event, there's a quite large range of tolerance on motor nameplates. This graph, which I won't go through in detail, is from the IEC, represents how they handle it. Excuse me. This is a table from ESA representing the same kind of information but in a different way. And you can see that there are actually quite large variations in percentage of parameters that are shown on typical nameplates. And in fact, these kind of tolerance, and here's how NEMA did a study and compared how NEMA and the IEC tolerances compared, and they're pretty similar. But in all cases, you can see these percentage numbers here are usually quite a lot larger than the typical kind of numbers you expect to see for tolerances on measured data from laboratory or even industrial grade instrumentation. What we do in our reports, here are a couple of examples of reports. Here's a measured inertia test report on the left, and here's a 5-run across the line start report on the right. We break down the actual percentages and some of these confidence limits that we saw earlier, comparing how well different estimates lay on top of each other from different sources. As a final confidence builder, we give you the ability with our tools to actually measure the rotor's inertia independent of the power supply system without running the motor. It's a non-running, it's a stationary type of a test. You can do it quite easily. And once you measure the inertia directly, you can then compare the inertia to the calculated inertia from the test results to use that as a further calibration and a confidence builder. All these testing methods and analysis methods are consistent with all the relevant standards, the IEEE, ESA MG1, and the IEC. They're all quite similar in their nature. The descriptions are a little bit different, but basically they're all recommending that testing be done the same way, and we adhere to those techniques. So thanks for watching. There are a lot more. In fact, there are more than 30 presentations in this series as part of the training course on the portable inertia dynamometer. We look forward to seeing you next time.